So today I thought we might go through this just to start off because I haven't done any videos for a long time. I just wanted to go through this, and I think this is a good way to like go through it, explain stuff, and read this. So what I'm going to try to do, what I'm actually going to try to learn today is actually the PostgreSQL text search. So let us go through this. Let's start. To implement full text searching, there must be a function to create a TSvector from a document and a TSquery from a user query. Also, we need to return a result in a useful order, so we need a function that compares documents with respect to the relevance to the query. It's also important to be able to display the results nicely. PostgreSQL provides support for all of these functions. Parsing documents. Postgres provides the function to TSvector. TS basically means text search vector, to text search vector for converting document to type. Text search vector data type. To text search vector regex config document text returns a TS vector. So you basically pass in this array with the config and also the document, I guess. Then here to TSvector parses a textual document into tokens, reduces the tokens into lexemes, and returns the TSvector text search vector, which lists the lexeme together with their positions in the document. So basically, if you have cat ate meat, cat will have 1, 8 will have 2, 8 probably will be reduced to eat, and meat will cat ate meat. Meat will be having the third number. So that's basically mean what they mean by positions. The document is processed according to the specified or default text search configuration. Here is a simple example. Select to TSvector is in English. It's going to take the English grammar. A fat cat sat on a mat. It ate a fat rats. Basically, this is a wrong thing, but I think they'll only consider this. As I said, 8 will come to the 9th position, which basically means 1, 2, 3, 4, 5, 6, 7, 8. This is the 8th position, but it shows 9 because 1, 2, 3, 4, 5. It's just okay, cool. Even though they have ignored, I think these numbers are not correct because cat should come as probably 2 because A is not there. Okay, maybe just the position A 1, 2, 3. That's the third one. Fat is coming in the 2. Okay, that's fine. Yeah, I think that this basically returns only the position, no matter like they're not reducing, even though they have neglected this on it 8 all those stuffs. I don't think that affects the position is the original position, so 8 should be 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, the example above we see the resulting TSvector does not contain the words on in it. The word rats become rat. The punctuation sign was ignored. The TSvector function internally calls a parser, which breaks the document into text tokens and assign type for each token. For each token, a list of dictionaries is consulted, where the list can vary depending on the token type. The first dictionary that recognizes the token emits one or more normalized lexemes to represent the token. For example, rats become rat because one of the dictionaries recognize the word rats is plural form of rat. For example, rat. Some words are recognized as stop words, which causes them to be ignored since they occur too frequently to be useful in searching. In our examples, these are on it. If no dictionary is in the list recognize the token, then it is also ignored. So I think it should be a large, very, very, very large dictionary. If you don't have a word that is in the dictionary, I think it's probably going to be ignored. Maybe a Gen Z word is probably going to get ignored. I don't know. Name and Gen Z word. Okay. In this example, that happened to the punctuation sign. In this example, that happened to the punctuation sign minus or a dash or whatever you call it, because there are in fact no dictionaries assigned for its token type space symbols, meaning sorry meaning space tokens will be indexed. Sorry, my voice changed because I was having uh, I don't know how to call it in English, meaning space tokens will never be indexed. The choices of parser dictionaries and which types of tokens to index are determined by the selected text search configuration. You can get figure, I think, what parser you want, what dictionary you want, what types of tokens do you want. Everything is possible when it comes to text search in PostgreSQL. You can do it whatever you want. I think this is a great add to for the PostgreSQL. I hope they promote this. It is possible to have many different configuration in the same database. It is possible to have many different configuration in the same database, and predefined configuration are available for various language. In our example, we use the default configuration English for the English language. The function setWeight can be used to label the entries of a TSvector with a given weight. The function setWeight can be used to label the entries of a TSvector with a given weight, where the weight is one of the letters A, B, C, D. This is typically used to mark entries coming from different parts of documents such as title versus body. Later, this information can be used for ranking of search results. So I can basically add, okay, that's pretty cool. Like, I can actually set weight to the elements. Like, if it is a title, I can actually set weight as A probably. Because to TSvector null will return null, it is recommended to use coalesces whenever a field might be null. Here is the recommended method for creating TSvector from a structured document. Update TSvector TTT set to TI set weight to TSvector coalesce title A. As I said, I knew it that title always have A. Keyword B, abstract C, body D. Body comes later. Coalesces, so that you don't, if you think this can become null, so better to pull coalesces. What kind of thing doesn't have a title? Here we have used setWeight to label the source of each lexeme in the finished vector, and then merge the label TSvector using the TSvector concatenation operator. Here we have setWeight to a label the source of each lexeme in the text. Okay, I have some kind of, okay, here we have used setWeight to label the source of each lexeme in the finished TSvector, and then merge the label TSvector values using the TSvector concatenation operator. Here we have setWeight to label the source of each lexeme in the finished vector. Okay, they are just talking about this, right? Okay, then merge the label TSvector values using TSvector concatenation. Okay, okay, this is the concatenation operator. Gives about this. Okay, yeah, I think, yeah. I'm pretty sure they just concatenate just to, like, I don't know, TT with TI. I don't know what is meant by TT. TT? Oh, okay, fine. I don't know. Parsing queries. PostgreSQL provides the functions to TSquery, plain to TSquery, phrase to TSquery, web search to TSquery. For converting a query to TSquery data type, to TSquery offers access to more features than either plain to TSquery or phrase to TSquery, but it is less forgiving about its input. Web search to TSquery is a simplified version of TSquery to TSquery with an alternative syntax similar to the one used by web search engines. Okay. Do you guys know? Do you know how the web searches uses the syntax with an alternative syntax similar to the one used by the web search engines? I'm not sure how the web search engine does, but I think maybe if you use web search to TSquery, you might know it. Not sure. Not really sure. Query text returns TSquery. You put just the query text and it returns the TSquery. To TSquery creates a TSquery value from query text which must consist single token separated by the TSquery operator and okay. So when I put this TSquery to TSquery, that returns and oh not. I was actually thinking the other way around, like I have to put the TSquery, but seems like if I put the query TSquery, it will the TSquery will have its operator. Okay, TSquery operators and O not followed by, let's say, cat8 mat. That means if I put the symbol there, cat should follow the mat, something like that. Possibly grouped by using the parentheses. In other words, the input to TSquery must already follow the general rules for TSquery input as described in section 8.112. The difference is that while basic TSquery input takes the tokens at face value, okay. In other words, the input to TSquery must already follow the general rules for TSquery input. In other words, the input, okay, I am zoning out right now and I have to read this again and again until you guys are familiar with this. I am doing this for you, not for me. Okay. In other words, the inputs to TSquery must always input to TSquery must already follow general rules of TSquery input as described in section 8.1.1.2. The difference is that while the basic TSquery the input takes tokens at a face value, the difference is while basic TSquery input takes the tokens at face value, to TSquery normalize each token into a lexeme using the specified or default configuration and discards any tokens that are stop words according to the configuration. For example, select to TSquery English the fat and the rat and this thing. To TSquery fat and rat. I think it just removed this, the fat. Okay. As in the basic TSquery input, weights can be attached to the lexeme to restrict it to match only TSvector lexemes of those weights. For example, select it to TSquery fat rats fat to TSquery, okay, fat O rats AB to TSquery fat O rat AB. Also, star can be attached to the lexeme to specify prefix matching. Not sure exactly, but yeah, to TSquery supan A star A into B AB supan A star AB. Such a lexeme will match any word in TSvector that begins with a given string. Okay, so I think if it is star, if you have started, if you have star, if you have stardom, if you have staring, I think that will match the word. I think if it should always have it should also have a weight of AB, I guess. I think. To TSquery can also accept single quoted phrases. This is primarily useful when the configuration includes a thesaurus dictionary that may trigger on such phrases. In the example, a thesaurus contains a rule supernova stars SN. To select to a query, did it supernova stars and crap. Supernova stars and crap. Okay. To TSquery. Okay. Cool. Still running. Yes. Supernova stars and to TSquery without quotes. To TSquery will generate a syntax error for tokens that are not separated by an and or followed by operator. Without quotes, to TSquery will generate a syntax error for tokens that are not separated by and or followed by operator. Plain to TSquery reconfig query text returns TSquery. Plain to TSquery transform the unformatted text query text to a TSquery. Okay, I am zoning out here again. I am trying to explain to you guys again so that you surely understands. So basically what it does is, if I put this single quotation and it will come like this, okay, that's super cool, I guess, in a sense. So actually it starts from here, super quotation with single quote, and there is a big I don't know where this exactly ends, but yes, then it will be SN trap, not crap. Without quotes, 2TS query will generate a syntax error for tokens that are not separated by and or followed by operator. Plain to TSquery config returns TSquery. Plain to TSquery transforms the unformatted text query text to a TSquery value. That is, the text is passed and normalized much as for vector. Then the AND operator is inserted between surviving words. For example, plain to TSquery, the fat and rat. Note that plain to TSquery will not recognize TSquery operators, weight labels, or prefix match labels in its input. To select plain to TSquery English fat and rat C, it won't recognize C as a weight, it will recognize it as a word. That's good to know. Here all the input punctuations are discarded. TSquery config, okay, cool. It behaves much like plain to TSquery. Phrase to TSquery behaves much like except that it inserts followed by operator between surviving words instead of AND operator. Also, words are not simply discarded but accounted for by inserting N operators rather than followed by operator. This function is useful when for searching exact lexeme sequences, since the followed by operators checks lexeme order, not just the presence of all the lexemes. Select phrase to query English the fat rats. Fat follows rat. Fat follows rat. That's, I think I am humiliating rat here because fat always follows rat. Okay, fat follows rat. Actually, rat follows fat. It eats rat. It eats fat. I don't know. Like plain to TS, the phrase to like plain to TSquery, the phrase to TSquery function will not recognize TSquery operators, weight labels, or prefix labels in its input. So if I put C here, the guy will say follow C. Web search to TSquery config returns TSquery. Web search to creates TSquery value from TSquery text using an alternative syntax which simple unformatted text is a valid query. Unlike plain to TSquery or phrase to TSquery, it also recognizes certain operators. Moreover, this function will never raise syntax errors, which makes it possible to use row user supplied input for search. The following syntax is supported. Unquoted text not inside the quote marks will be converted to terms separated by AND operators as if processed by plain to TSquery. Quoted text inside the marks will be converted to terms separated by operators as if processed by phrase to TSquery. The word O will be converted to the the word O will be converted to the O operator. Okay, if I put O, the text inside the quote marks will convert to the terms separated by followed by operators as if processed by phrase to query. Text not inside the quote marks will be converted to terms separated by AND operators as if processed by plain. Okay, cool. This is cool. This is O. If I put O, I think if the a dash will be converted to the not operator. Okay, if I put a dash there, I think that might be converted to not operator. Probably I have to check this one. Other punctuation is ignored. Yeah, other punctuation is ignored. So like plain to TSquery and phrase to, so if there is another punctuation, it will be ignored. Okay, so like plain to TSquery and phrase to TSquery, the web search to TSquery function will not recognize TSquery operators, weight labels, or prefix match labels in its input. Wait query will not or prefix match labels in its input. Select web search query English the fat and rat. It will say it has a minus, so it will become not crap, and it will say supernova stars. There's a quotation, so it will there's a single quotation. It will show supernova star. Dun. Web search TSquery sad cat or fat rat. Web search to TSquery sad cat or fat followed by rat. Web search to signal segmentation fault. English signal segmentation fault. So guys, can you guess it? Of course, here's the answer. Signal and uh, just so signal just an segmentation, so it comes like this, so it will come within this segmentation segment. It's the root word segment followed with fault. Then we go to the web search TSquery English. It starts here and ends. I don't know why there is an empty quotations. So dummy comes under a quotation. This is ignored, and the query is coming also because it's just a word query followed by I think this is ignored because this is actually the query, the text query. This is not the TSquery. This is going to get converted to TSquery. So this is basically a word. This is going to get ignored. Yeah. Cool. Ranking attempts to measure how relevant documents are to a particular query so that when there are many matches, most relevant ones can be shown first. PostgreSQL provides two predefined ranking functions which take into account lexical proximity and structural information. That is, they consider how often the query terms appear in the document, how close together the terms are in the document, and how important is the part of the document where they occur. However, the concept of relevancy is vague. Very application specific. Different application might require additional information for ranking, document modification time. The built-in ranking functions are only examples. You can write your own ranking functions, add and or combine their results with additional factors to fit your specific needs. The two ranking functions currently available are TSRank, weights, float, so you can actually pass in weights with a float. Vector, TSvector, okay. You pass in the TSvector and the TSquery, and normalization integer returns float 4. Float 4 is basically I don't know what is float 4. Basically it's a number, but I don't know what is a float 4. I know float, I don't know what is float 4. Maybe it's the how it has 4 decimals. I guess you can only put 4 decimals. Is that what float decimals? I don't know. I don't have an idea. Rank vectors based on the frequency of their matching. Am I still running? Yeah, still running. Still running. That's great. Okay. The two ranking functions currently available are, okay, I said that, ranks vectors based on the frequency of their matching lexemes. Rank vectors based on the frequency of their matching lexemes. TSRank CD weights float TSvector normalization. This function computes the cover density ranking for the given document vector query as described by the Clark Cormack two thoughts relevance ranking for 1-3 terms queries in the journal information processing management 1999. Cover density is similar to TSRank ranking, except that proximity of matching lexemes to each other is taken into consideration. This function requires lexeme positional information to perform its calculation. Therefore, it ignores any striped lexemes in this TSvector. If there are no unstriped lexemes in the input, the result will be 0. Okay, that might be a case. Okay, right? I don't know. I'm just saying this. This function requires a positional information to perform its calculation. So if there is no positional information, there might be an issue. Therefore, it ignores any striped lexemes in the, okay, striped basically means striped lexemes. What do you mean by that? The one which has, it ignores striped lexemes. That basically means, are they saying that, let's say, if let's say like this, where was that? Yeah. Where was that? Yeah. Segmentation got stripe to segment. Is that what you mean by a stripe lexeme? I'm not sure. Uh, okay, stripe lexemes. Okay. For more information about stripe function and positional information, so I think you should have used this stripe function to get a stripe lexeme. So I think we are good to go. I think there won't be an issue, but I do have a problem. The main thing that I'm learning about this is that there was a issue with this TSvector search. I have to remove it, but at some point I have to use it because to get this ranking actually, which I doesn't actually get 100%. This is kind of over the top for me. Like I'm not sure whether I get this the whole stuff, because ranking attempts to measure how relevant documents are to a particular query, so that when there are many matches, most relevant ones can be shown first. So it's basically ranking. I don't know how it happens. It has two ranking functions, but what do you mean by documents? Like, do you actually go through the other documents? Like, do I have to create a vector on the one that I have? Let's say I have a text of like text that talks about the paragraph that talks about cat, and then the query is kitten, and how does it like kind of work? I don't know. Like, how does it rank based on, like, let's say I put a kitten and like there are articles on kitten, and the one that I actually want is cat, but how do you like how do you rank it actually? Like when you have, it's going to get ranked way below, and I think not sure how it exactly happens. Maybe I have to read this, that document that they were mentioning, like where is it? Yeah, relevance ranking for 1 to 3 term queries in the journal information processing management in 1999. Huh. See section for more information about the strip function and positional information in TSvectors. For both these functions, the optional weights arguments offers the ability to weigh words instances more or less heavily depending on how they are labeled. The weight array specifies how heavily to weigh each category of word in the order: D weight, C weight, B weight, A weight. If no weights are provided, then these defaults are used: 0.1, 0.2, 0.4, 1.0. If no weights are provided, then these defaults are used. So if I don't provide a weight, these are the defaults. How comes? Okay, maybe not in this order, I guess. Like if this is the order, like whatever I give, they're going to give this weight. I'm not sure. Typically, weights are used to mark words from special areas of the document, like the title or an initial abstract. So they can be treated with more or less important than words in the document body. Okay, since a longer document has a great chance of containing a query term, so this is the issue. So we are using two types of thing. One, we are using embedding search, and the other one is this. So I think I have to go through the embedding as well to understand like what's the difference and how they actually like come up with this thing. So basically I have to store this in some kind of I don't know, like query. Yeah, I think so. Since a longer document has a greater chance of containing query term, it is reasonable to take into document size. 100-word document with 5 instances of search word is probably more relevant than a 1000-word document with 5 instances. Both ranking functions take an integer normalization function. Both ranking functions take an integer normalization option that specifies whether and how a document's length should impact its rank. The integer option controls several behaviors, so it is a bit masked. You can specify one or more behaviors using for example 2 or 4. 0, the default ignores the document length. 1 divides the rank by 1 plus logarithm of the document length. 2 divides the rank by the document length. 4 divides the rank by the mean harmonic distance between the extents. I don't get this, but I'm just reading this. 8 divides the rank by the number of unique words in the document. 16 divides the rank by 1 plus logarithm of number of unique words in the document. 32 divides the rank by itself. So what they actually trying to say here is like, I don't know, there's kind of max that I don't actually understand, since no longer document has a greater chance of containing. Okay, so they are actually, what they're saying is, I can say that for you, for you can read this quickly, read this, like 100, if you have 100 with 5 instances of the search word, it's good, but if you have 1,000 with just 5 instances, that's bad. That's basically that they are trying to say here, I guess. 32 divides by the rank itself plus 1. 32 divided by the rank itself. If more than one flag bit is specified, the transformation applied in order listed, in the order listed. It is important to note that the ranking function do not use any global information, so that it is impossible to produce a fair normalization 1% to 100% as sometimes desired. Normalizations option 32 rank divided by rank plus 1 can be applied to scale all ranks into the range 0 to 1, but of course this is just a cosmetic change. Of course this is just a cosmetic change. It will not affect the ordering of the search results. Here's the example that selects only the 10 highest ranks matches. Okay, I didn't understand any of this, but if I get this, maybe I can get this example and like probably like work my through myself to an understanding, which is going to help you, not for me. I'm not doing this for me. Just kidding. I'm just trying to learn. So let's try to figure out, like, I didn't get any of the thing that they said here. Like from the starting itself, I didn't understand ranking at all. So I think this is the best chance. This is my last chance. So you get the title, you select the title, then the rank. Okay, as rank. So this is the rank. Okay, that's the rank. Where query is equal to text search. Okay, here's the text search query. Okay, query is coming from somewhere down the parameter through the the callback hell, not the callback hell. It's coming from the, actually it's coming from here, it's coming from the prop drilling through to Java. It's coming all the way to here. Okay, it's coming here. Okay, query and text search. Okay, order by rank descending, limit 10. So 10 is all that you're going to get. So if you think about it, descending 3.1, the largest one. Neutrinos in the sun, that's the rank. 3.1 is the rank this guy gets. I don't know what the search query, it would have been happy to have that, but you're going to get the 0.81 as the last one. So get on with it. I don't know which one is the actually. This is the sample using the normalized ranking. Okay, here's an example that selects only 10 highest rank matches. Okay, this is the normalized ranking. Title TSRank. Okay, this is the normalization, I guess. 32 divided by 2 rank plus 1 rank. From apport to TSquery neutrino o dark and matter query. Okay, that's the query. I guess. Okay, then we have the query here. Neutrino, dark and matter. Query text search. So you have all this stuff. So neutrino is here. That is coming as the first one. So neutrino has 0.75. That the one that has the highest rank comes first. So neutrino, boom, 0.7. Neutrino again. So I think dark and matter, it's not there. Oh, dark and matter. Dark, here it is. Dark, yeah. Hot gas and dark matter. Neutrinos, I'm not sure why they actually have, but I can just show you that this doesn't have any of these words. So it's coming as 0.45. The rank is lower. The lower the rank, the lower your rank is. It's basically not start from first. If you are the 10th rank here, if you have the 75th rank, you are good. But if you have the 45th rank, you're the class last. I'm just kidding. Like you come, this is the other way around. So that's why we have the higher the rank you have, the higher you are. Relative to related or to this query. Ranking can be expensive since it requires consulting the TSvector of each matching document, which can be an IO inbound input output bound, therefore slow. Okay, ranking is slow. Unfortunately, it is almost impossible to avoid since practical queries often result in large number of matches. Highlighting results. To represent search results, it is ideal to show part of each document and how it is related to the query. Usually, search engines show fragments of the document which with marked search term. PostgreSQL provides a function TSHeadline that implements this functionality. TSHeadline config document search T returns. TSHeadline accepts the document along with a query and returns an excerpt from the document in which from the query are highlighted. Specifically, the function will use the query to select relevant text fragments and then highlight all words that appear in the query, even if those words position do not match the query's restriction. The configuration to be used to parse the document can be specified by config if config is omitted. The default text search configuration is used. If an option string is specified, it must consist of a comma separated list of one or more option pairs. The available options are sweet, still working. Yes, I don't get this. TS headlines accept a document with query and returns an excerpt from the document in which terms from query are highlighted. Specifically, the function will use the query to select relevant text fragments and then highlight all the words in the query. Even if those word position do not match the query's restriction, the configuration to be used to parse the document can be specified in config. If config is omitted, the default text search configuration is used. The option, if an option string is specified, it must consist comma separated list of one or more option equal to value pairs. The available options are max words, min words, integers. These number determine the longest and the shortest headlines to output. The default values are 35 and 15. Short word, okay, that's max and min. Then there's short words. Words of this length or less will be dropped at the start of the end of the headline unless they are query terms. The default value of these 3 eliminates common English articles. The default value of 3 eliminates common English articles, so they basically want to eliminate whatever that is below the short word. Highlight all boolean. If true, the whole document will be used as the headline, ignoring the preceding 3 parameters. The default is false. Max fragments integer, maximum number of text fragments to display. The default value of select 0 selects a non-fragment based headline generation method. A value greater than 0 selects fragment based headline generation. See below. Start cell, stop cell strings. The strings with which to delimit query words appearing in the document to distinguish them from the other excerpted word. The default value is B and B, the bold tag, I guess, which can be suitable for output. Fragment delimiter. When more than one fragment is displayed, the fragments will be separated by the string. The default is ... These option names are recognized case insensitively. You must double quote string values if they contain spaces or commas. In non-fragment based headline generation, TS headlines locates matches for the given query and chooses single one to display, preferring matches that have one more queries within the allowed headline length. In fragment based headline generation, TS generation locates the query matches and splits each match into fragments of no more than max words for each, preferring fragments with more query words and when possible stretching fragments into give me a second. If in non-fragmented based headline generation, TS headline locates matches for the given query and chooses a single to display, preferring matches that have more query words within the allowed headline length. In fragment based headline generation, TS headline locates the query matches and splits each match into fragments of no more than max words each, preferring fragments with no more query words and when possible stretching fragments into surrounding words. The fragment based mode is thus more useful when the query matches span large sections of the document and when it's desirable to display multiple matches in either mode. If no query matches can be identified, then a single fragment of the first min words the documents will be displayed. Let's go to the example. So you put the TSX line. The most common type of search is to find all documents containing given query terms. Return them in order of the similarity to the query. To TSquery English query and similarity. So you have this and the TS headline. So query, you have it. Similarity here you have it. Containing given B query terms. And return them in the order. Okay. I think that headline is basically highlighting. So what it will do is you put these two the guys will be highlighted. Just the kind of decoration that you can add, just nothing much. You put this, select TS headline and search blah 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 this search and term, and you put this all those stuff here, and you'll get this many times. You'll get ignored something if it is in word. Start cell, I'm not sure what it is, but things will happen. Likewise, maybe this search start cell, start cell is coming here. What happens? This search, okay, stop cell, something like that. Yes, adjust to desired here. Original document, not headline uses the original document, not a TSvector summary, so it can be slow and should be used with care. So carefully not use it. I don't think you might need it. I don't know. Probably you're not going to do it in the front end, so I don't think you might need it. You can do it actually. I think you don't need it. Yes. Submit your corrections. If you see anything wrong in the documentation, that is not correct, which I said wrong, does not match your experience with a particular feature or requires further clarification, this is great. Cool, really cool. See you on the next one.